Okay, welcome back everybody. Unit 1, video number 3. Last time we were talking about the mean and median and mode, so basically measures of middle, central tendency if you will, and we also were talking about measures of spread, like the standard deviation, range, variance. We also discussed maybe how to interpret standard deviation and how it relates to Chebyshev's theorem and the empirical rule. In this video, we're moving on to some other statistics where we talk about measures of position. We'll discuss z-scores, percentiles, quartiles, and we'll even introduce a new plot that incorporates some of these things. So, diving right in, we'll start talking about the first one here, a measure of position called a z-score. We're going to use these in several ways throughout the course. We've already sort of discussed this topic a little bit when we were talking about the empirical rule and Chebyshev's theorem. With each score in any data set, you can calculate how many standard deviations that score is above or below its mean. So, for example, I could have a score x. It's equal to the mean plus some number of standard deviations. I used a population example. If we rearrange this formula, we'll get x minus mu equals z sigma. So x minus mu divided by sigma equals z. Z is some number of standard deviations that a particular score is away from its mean. It can be positive or negative because you can be above the mean or below the mean, and the sign will tell you which direction it's in. Our use of z-scores, first we will use them to differentiate between ordinary and maybe unusual values. We could use them to differentiate scores from different populations that might have, say, different units or different means and standard deviations, because the z-score is another one of those dimensionless statistics, kind of like the coefficient of variation. So it's good for comparison that way. And a little later, we'll use it to do transformations so that we can determine probabilities from a normal distribution. But for right now, we're basically just going to use the formula and start to understand what a z-score is. I think it will help us to get a better feel for standard deviation as well. Most likely, we will be using the sample form x minus x bar over s, because most of the data that we deal with is sample data. We could restate the empirical rule and Chebyshev's theorem using z-scores. Basically, I drew the same picture that we had for the empirical rule, and this value here is indicating that I'm one standard deviation above my mean. And then this value here is one standard deviation below the mean. And we learned that when you have a bell curve, that 68% of our values lie within that range. So we can just restate those theorems within 2 standard deviations of the mean, or within 2 z-scores of the mean. We get 95% of the data, and if we have a z-score from -3 to +3, then we have 99.7% of our data. I guess this axis is a z-axis. You'll notice that the mean has a z-score of 0, which makes sense. If you have x minus x bar over s, how far away from the mean is the mean? Well, if you replace your score here with x bar, you get 0. So the mean is no standard deviations away from the mean. One of the uses of this then is to say, help distinguish between what is likely to happen and what is unlikely to happen. We might use this to make decisions later. If you have a score that is between -2 and +2, that's a pretty typical score because 95% of all our values lie in this range. Anything outside of that range is starting to be unusual because you're in sort of that last 5%. We're sort of classifying 5% of our data is somewhat unusual. So whenever you encounter a score that ends up outside of that -2 to +2 range, then you can start to, maybe do further investigation. Why did such a thing happen? Did you just get unlucky? Of course, I said this is a guideline. This is mostly because we could only really apply this when we know we have something that has a bell shape. When we don't have a bell shape, I think we should maybe extend these values out. Maybe our usual range should be extended to something like -3 to 3, and our unusual would then be outside that range. So if you're under -3 or above +3. The reason I'm saying this is in Chebyshev's theorem, we said that we can only guarantee that at least 89% of our data is in that range. So we're now declaring, 11% of our values are potentially unusual. But I think this is a rather extreme case. Generally, the percentages you have to draw sort of a weird distribution to get anywhere down as low as 89. Usually it's much higher. So I think this is a pretty good rule to go by. Generally, if you know that your data is bell-shaped, maybe use a rule of -2 to +2. And if you know that it is not bell-shaped, use -3 to +3. Or if you don't know the shape at all, use -3 to +3 to be more conservative. In quality control situations, you'll often hear the buzzword Six Sigma design. What they're referring to is exactly what we're talking about right now. This interval right here is 6 standard deviations wide. It's 3 standard deviations below the mean and 3 standard deviations above the mean. Whenever you're outside of that range, that's when you have reason to do investigation. So that's just something that may be coming up later in the course. Just thought I'd mention it now in case some people have backgrounds in this. Little, simple example using Z-scores. We're interested in, Michael Jordan here. Is he a tall guy for a typical adult male? One way we can answer that question is to calculate Michael Jordan's Z-score. So his height is given there. He's 78 inches tall. The mean of the whole population of adult males in the North America is 69.5 inches, at least according to Wikipedia, and the standard deviation is 3 inches. So let's calculate Mike's Z-score and determine whether or not he's unusually tall. In this case, I was able to use mu and sigma for the mean and standard deviation, even though I don't think anyone ever collected my height to determine this. I feel that they've been studying adult males long enough in North America that these numbers are probably, at least to, one decimal place, are probably pretty stable. So I'm okay to use mu and sigma here. Mike is 78, the mean is 69.5, the standard deviation is 3. Notice how the numerator is inches, the denominator is inches, so that will all cancel out, and we get a number of 2.83. Is he tall? Well, it depends on what rule we go by. Up above there, we said if it's outside of this -2 to +2, yeah, he's kind of unusually tall. If we go by the second version, we say maybe not super tall. He's getting there. I think with this situation, we can pretty much imagine that heights of North American males probably look pretty bell-shaped. It's skewed a bit because you can't be under 0, but you could be, 20 feet tall. So the real shape of the thing has a bit of skewness to the right. Actually, I don't think anybody's maybe above 9 feet. I haven't looked up what the tallest person is. But I would expect it to be bell-shaped or maybe slightly skewed to the right. Because of that, I think we can apply the -2 to +2. This value is more than 2 standard deviations. Above the mean. So, yes, he's tall. But as a basketball player, is Michael Jordan tall? Again, going to Wikipedia, we go and find the mean height of an NBA player, and they tell me it's 6 feet 8 inches, which translates to 80 inches, and the standard deviation is 3.9 inches. Again, I'm using population values. I think we can get away with that. They probably know the heights of NBA players pretty precisely. Repeating our Z-score calculation, Mike is still 78 inches, but now the mean has changed. The mean of NBA is 80 inches. The standard deviation is 3.9 inches. So we end up with a Z-score of negative 0.51, if you want to go an extra decimal place there. So in this case, is he a tall basketball player? No. Is he short? No. He's only half a standard deviation below the mean. So he's just a typical basketball player, I would say. Moving on to another measure of position, we'll talk about percentiles and quartiles next. You've probably heard of these before. If you've ever had any standardized testing, maybe this is how you received your score. Percentiles and quartiles are just values that separate the bottom portion of the population from the top portion of the population. So it's basically just a cutoff. On a standardized test to get into graduate school, I scored in the 98th percentile on the math portion. Yay for me. It doesn't mean that I earned 98% on the test. It means that I beat 98% of the people that also wrote that test. On that same test, I had to write a verbal section, and I scored in the 53rd percentile. Again, I didn't get 53% on the test. It means I was only able to beat 53% of the other people that were writing the test that day. Those are percentiles, and that's a way to use them. Quartiles are just special percentiles. Basically, you're just breaking your data set into quarters. First quarter, second quarter, third quarter, and we'll denote those with subscripts Q1, Q2, Q3, and percentiles will denote it with a P with a subscript as well. So my math test score was 98th percentile. My verbal section was 53rd percentile. I'm not really proud of that. I'm not even really proud of the 98th percentile in the math section. This was a general test to get into graduate school, so people that were, philosophy majors or English majors or business majors, or basically everyone going into grad school was taking the same test. So it wasn't really fair that a math major was taking a math section, but I felt it kind of got balanced out because I was going up against English majors and history majors, and maybe that's why my verbal score was not so hot. We generally don't talk about a fourth quartile because that would be the 100th percentile, which is rather hard to define. A little example here, it's similar to what I was just saying about, my graduate school accolades. On Math 12 provincial exam, Bill scored in the 75th percentile. Again, he didn't get 75% on the test. Maybe he got 50% on the test, but he still beat 75% of the people that wrote the test that day. So he's P75, or we could also call that Q3, the third quartile. How do we determine these things? Well, it involves sorting. I made a little flow chart here. There's more than one way to determine these things, and it's not well agreed upon. Different textbooks will do this in different ways. So if you got tired of my video on this and started watching a Khan Academy video, they might do their percentiles and quartiles slightly different, but this is the way that we will do them in this course. So let's stick to this. I know there may be even better ways. This way, I made a little flow chart to help us figure these things out. But the most important step of the whole process is sort the data. On the midterm, maybe I'll give you a data set where I'll be really mean. The first 3 values will be in order, and the last 8 values will be in order, but the middle 10 values will be all mixed up. And then when you'll look at it, you'll think, oh, those look like they're in order. And then you'll go to determine your quartiles and percentiles, and you'll get it wrong because the data will not have been sorted. You'll have broken the first rule of forgetting to sort. So after you've sorted your values, you then want to locate where the cutoff should be. I'm calling it L for location. Basically, if you want the 93rd percentile, you do 93% of however many values you have, and that's roughly the spot. It's not exactly how we're going to choose it. That's where this decision comes in here, where if our location ends up being a whole number, we'll do one thing, and if our location ends up being a fractional number, then we'll do something else. So if it's a whole number, we're going to look at that spot in the list and then take the average of that one and the next one, basically bumping it up a little bit. If it's not a whole number, if it's, the location spot is the 92nd point third spot through the list, we're just going to round it up and take the 93rd spot in the list. In both cases, we're making an effort to sort of bump it up a little bit. Well, by doing it this way, we're sort of ensuring that if you end up in the whatever percentile, the 93rd percentile, that you actually did beat 93% of the people that wrote the test that day. So by bumping it up, we're kind of just doing a small adjustment to it, making things conservative in that way. Now, there are other ways to do it. If you end up partway between values, maybe we could do interpolation or something. So this is a rather crude way of doing it, but it does just simply err on the high side. We'll do an example here, or hopefully this will make sense. Remember good old supplier B. They were the 2x4 supplier, and they had defects in their boards. This is the raw data from the stem and leaf plot. Back when we looked at this data initially, we found the median of it. So we've already found a percentile. The median is the 50th percentile. So we could repeat that. The median, which is Q2, which is the 50th percentile. Remember, we had 20 values. So we went halfway through the list, which was between the 10th and 11th spot. Well, where are the 10th and 11th spots? We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And remember, we had 41.5 for that. And these were defects in groups of 50 boards. Now, the new way we'll do this is we will locate the position of this. So in this case, we're looking for the 50th percentile. So 50% of however many there are in the list. 20 items. 50% of 20 is 10. Now that's a whole number. So we have a little rule that says if your location is a whole number, find the mean of that one and the next one. A big mistake that lots of students make is they'll just write the 50th percentile equals 10. They will forget to go and look for the 10th value in the list. For the 25th percentile, you can see that's already done for us here. We locate the position of the 25th percentile, which is spot number 5. So we go 5 values into the list. I guess that's here. Here's the 5th value. So because it's a whole number, we're going to find the mean of the 5th and the 6th. So it's going to be the mean of, did I count that wrong? I did. I should edit this out. I had it right the first time. Here's the 5th and 6th. So it's between 32 and 36, and the average is 34. I'm just going to leave it in there. You can see me make mistakes. 75th percentile, 75% of 20 things is 15 items. Go 15 positions into the list. You'll find that it's between 49 and 50, so our value is 49.5. The 92nd percentile is maybe a little, at least this one's different, in that 92% of 20 things is 18.4. Now we don't have a whole number for our location, but if we go back to our flow chart, is L a whole number? The answer is no. So we're just going to round it up and choose the value at that spot. So in this case, our position is 18.4 positions into the list, and we're going to round it up to the 19th spot, and the 19th spot is right here, which is than 69 defects in 50 boards. Excel doesn't do it using the same method. Some other stats programs do it even different than Excel does, but most of them attempt to go part way through the list. So they would go 0.4 of the way between 69 and 72 and get a slightly more, accurate estimation of what this should be. But when you have large data sets, the method doesn't really matter. If you have 10,000 items in the list, these subtle, should I round it up or should I go partway between two values, won't matter much. When these come into play are on the small data sets, like the ones that we tend to give in stats classes, then the way we decide this will matter a little more, particularly when you have under 100 values. You can imagine, how do I find the 93rd percentile and the 94th percentile in a set of data that only has, say, 12 values? I mean, there aren't enough values in the list to have different values for each of these. So say the 93rd and 94th percentile would probably be the same number. But that's just a problem that you run into with small data sets. We can use these quartiles to create a new plot. One plot is called the box and whisker plot. I'm usually just going to say box plots. They plot 5 numbers. So they're basically 5 dots on a number line. They are the min, Q1, the median, Q2, and the max. Basically, we're just going to plot those 5 values on a number line and then create a graphic from it. So you have your large data set, you find these 5 numbers, you draw a scale, and then you just plot those 5 dots. The rest of it is just for show. You'll notice there is no y-axis drawn on this picture because there isn't one. We don't need to have one, which is one of the reasons why we might use this plot, is that it's nice that you can stack them above each other and not have to have a limit as to how many you can do. What are you supposed to get from a plot like this? Well, things you can quickly see is you can see if either of the whiskers ends up being particularly long. Like if you had a whisker sticking way out this way, you go, well, maybe that's an unusual value. So it's a way to help you identify if there are outliers in your data set. That's one use. You can see if the data is symmetric. If your whiskers on each side are roughly the same length and your median is kind of in the middle of the box, it's an indication that your data is fairly symmetric. No guarantee, but it does help with that sort of symmetry interpretation. The next thing, maybe the most important thing, is you can see how wide the box is, like this distance from Q1 to Q3. We even give that a name. It's called the interquartile range, IQR. It's Q3 minus Q1, the width of that box. A narrow box means your data isn't spread out very much. A wide box means your data is spread out quite a bit. So this is like another version of standard deviation. It measures your data variability. And it isn't affected at all by outliers because Q1 and Q3 aren't affected by outliers. If there's one strange value in your data set, it doesn't affect the positions of the quartiles. So those are some common uses of this and what we're basically supposed to see from it. Our example, you probably recall supplier A and B. We had just calculated the quartiles for supplier B. Hopefully these numbers match. For supplier B, we had just found that Q1 was equal to 34. The median was 41.5, and the third quartile was 49.5. These were all defects per 50 boards. We could go ahead as an exercise. I leave it to the reader to go and determine the quartiles for supplier A, and hopefully you will match these numbers here. The min and max could easily be found for those data sets as well. I forget, from supplier B, if we went back to our example, we can quickly find our minimum was 21 and our maximum was 72. So we can see that on this plot here. The min was 21 and the max was 72. I made a scale that went from 15 to 75, and then I just plotted the number 21, the number 34, the number 41.5, 49.5, and then 72 based on that scale. Then I started connecting the dots. Q1 and the min get connected, Q3 and the max get connected. The height of the box, I could have drawn any height. Maybe this is the golden ratio or something. So I just made heights for the other three, and I finished off the box. So this is a plot that you can actually do by hand. I've actually asked students to do these on midterms and finals and such, just because it is something that you don't necessarily need a computer to do, and it can still look okay without needing a lot of straight edges. Supplier A is on the plot as well. Notice that there's no y-axis here, so I could have stacked them up in either order. It doesn't matter which way I do it. And I'll even make a little legend here. We'll color this in and call supplier B the red one. So yeah, looking at this plot, we can quickly see that the box for supplier B is much narrower than the box for supplier A, indicating that supplier B has a more reliable product. We'll also see that the box for supplier B is shifted towards the lower values, which in this case is desirable as the values are number of defects. So low scores are better than high scores. So simply by looking at this plot, we can see that supplier A is better, or supplier B is better than supplier A. A few times throughout this, I've been mentioning another term. I've been mentioning outliers without really defining it. Outliers are sort of suspicious scores or unusual scores. And it's a really difficult topic to discuss because there isn't a solid rule as to what to do with outliers. If you have a data set that has one value that's completely different from all the rest, maybe way higher, what should you do with it? Should you delete it? Should you include it? It sort of depends on your situation. Do you suspect it was an error? Then maybe it's possible you could delete it. If it's something that just occurs naturally, then you probably should leave it in there. But again, this is something that is, rather philosophical and also situation dependent. If you're doing a medical study and, you test 10,000 patients and 2 of them, die, do you delete those 2 people that died? That becomes a big issue with this sort of outlier topic, but what we can do is come up with an objective way as to what to call an outlier, and then from situation to situation, we can decide what to do with them. So one way to determine outliers, we sort of already covered when we were talking about z-scores. We said that if you had a z-score outside of 2 standard deviations away from the mean, and you had a bell curve, that was unusual and a potential outlier. When we didn't have a bell curve, we widened it and said maybe we should use a criteria of 3 standard deviations. Now, the concept of z-score is maybe a little more foreign to people. So another criteria has been developed where we use quartiles to basically decide where our outliers go, or may be. We determine these cutoffs called fences. We'll have inner fences and outer fences. So basically 2 criteria. So here's a box plot drawn here, and I've included some inner fences. These are these yellow dotted lines. Any value that falls in the yellow dotted lines is, a typical value. But then once you get beyond the upper yellow or the lower yellow dotted line, you have a possible mild outlier. Maybe we don't do anything about them because they're considered mild outliers. Once you get to these more extreme fences, we'll call them the upper fences, then we start to encounter extreme outliers. So if you have values, if you had a score up here, that would be an extreme upper outlier. And if you had one down here, that'd be an extreme lower outlier. And if you had one at score, say here, that would be a possible lower outlier. So that's how we will use these to identify outliers in our data set. The fences are just formulas. The inner fences are based off of a factor of 1.5 interquartile ranges. So if you're more than 1.5 interquartile ranges sort of away from the box. So here is your box. If you end up with a score that's 1.5 interquartile ranges either above or below the box, then you start to be a mild outlier. And the 1.5 factor is just a standard that we've agreed upon. It's sort of like using the number 2 or the number 3 from Chebyshev and empirical rule. We can go out to 3 interquartile ranges, and that's when we determine extreme outliers. So think of 1.5 interquartile ranges as sort of like a z-score of plus or minus 2. And then think of 3 interquartile ranges as corresponding with a z-score of plus or minus 3. If you look at this plot, I think I drew it mostly to scale. Remember what the interquartile range is. It's the width of the box. So it's this width that I'm scribbling here. If I have 1.5 of those above Q3, so if I draw a box and a half, I end up at that fence. And if I draw 3 of these boxes, then I end up at the outer fence. So I know I did that pretty poorly, but I think you get the idea. Of course, if I were talking to you right now, you'd be nodding or shaking your head. So basically, we're going to just calculate these values. Sadly, Excel doesn't have a nice function built in called, inner fence or upper fence. So we'll have to calculate these things with a custom formula. But that's not so bad. Back to supplier B. I'm sure we're getting tired of that group of data by now. We have our defects in 50 boards. Remember, we had our quartiles already determined. They were defects per 50 boards. We can calculate the interquartile range, which is Q3 minus Q1. In this case, it turns out to be 15.5. Then I just basically plugged everything into the formulas for the inner and outer fences. I didn't write it out for you here. I think that you can follow this. So basically, we calculate our fences and we can determine if there are any outliers in our supplier B data. So our inner fences for supplier B were at 10.75 and 72.75. So I don't even have a scale large enough to include some of these values. 10.75 is somewhere down here, very crudely. 72.75 is somewhere up here. If you look at our supplier B data here, this supplier B is the upper plot, you'll see that none of the values in that data set are outside of these inner fences. This is the upper inner. I don't even need to calculate the outer fences because all of the data is already within those fences. But they did anyway. Minus 12.5, which is off the scale. You can't have negative 12 defects, and 96. Way off the chart here. So we don't have any extreme outliers. This range is where we'd find mild, and this is where we'd find extreme. And we can have the same on the lower end as well. Negative 12.5 is off the page. And we don't have to be concerned with any values there. I could ask you now, does supplier A have any outliers? And if you look at it, their maximum is right here at 79. So it might be tempting to say, yes, supplier A has an outlier at 79, but we'd be wrong. The reason for that is that the fences that we calculated were using the supplier B quartiles. So these fences that we drew, or I wouldn't say drew, that we scribbled onto this plot, only apply to the top graph, the top box and whisker plot. So this 79 is not violating likely its upper inner fence, because when you look at the supplier A data, the box is so much wider that its upper fence will be quite a bit further out anyway. So I don't think there will be any outliers in supplier A either. But go ahead and calculate the fences for that data as well. I made an Excel, a little template that will help calculate generate these box and whisker plots, and they include the fences. So you'll get to take a peek at one of those when we're doing a lab sometime. I think that's probably a good place to end this lecture. So let's call it a day, and in the next one we'll do some fun stuff where we see examples of some bad statistics. But for now, we can sign off, and I will see you next time.